can we generalize the ideas presented before for a general square matrix A with a general matrix R? Suppose you have a matrix A of dimensions n by n, and also suppose that the rank of this matrix is R. The rank of A is equal to some value R. What would be the singular value decomposition for this matrix? Again, I want the matrices U and V to be orthogonal matrices, and I want the matrix sigma to be a diagonal matrix. In this case, we can see the following: A multiplied by V. We can here put V1, V2 up to VR, the rank of the matrix, because we are sure to have at least R independent perpendicular vectors for the row space, since R is the number of independent rows. Now this matrix should be an n by n matrix. So we need to complete those vectors right here by perpendicular vectors, and we can use vectors from the null space since the null space is perpendicular to the row space, and so any vector in the null space of the matrix is perpendicular to the whole row space of the matrix. So from R plus 1 up to n, we can have VR plus 1 from the null space up to Vn also from the null space as vectors inside this orthogonal matrix V. Then here we can put the matrix U. For the matrix U, I can also have U1, U2 up to UR, because I can have R independent perpendicular bases for the Coulomb space, since the number of independent coulombs is always equal to the number of independent rows. After that, I can complete this matrix by vectors from the left null space from UR plus 1 up to UN. Then for the matrix sigma, I can have the following. I can have here sigma 1, sigma 2 up to sigma R, and here from sigma R plus 1 up to sigma n, I can put zeros, and zeros here and zeros here, and in this way I can have the following. I can have that A V1 is equal to sigma 1 U1, A V2 is equal to sigma 2 U2. This will continue until we finish all the vectors from the row space of our matrix A. So A VR is equal to sigma R UR. After that, all the remaining vectors will belong to the null space, and so A VR plus 1 is equal to 0, which is equal to 0 multiplied by UR plus 1, again up to Vn, so that A Vn is equal to 0, which is equal to 0 multiplied by Un. This means that we could still decompose our matrix A to be equal to U sigma V transpose for a general singular or non-singular square matrix A. In the next video, we will start generalizing this to even rectangular matrices.